All right, the last thing we're doing is something called combustion analysis. And again, this is a typical analysis that would be done in a lab to determine the composition of an unknown substance. And in this case, it's an unknown substance that contains carbon, hydrogen, and possibly oxygen. And so just to give you a little background, so you'll kind of know where these values that we're going to use are going to, where they come from, we have a substance and they put it in like a little chamber here. Okay, we're going to feed some oxygen into that chamber and burn the substance. Okay, the products of that reaction are going to be passed through a water absorber and a CO2 absorber. If you remember from some just basic chemistry, when we burn a hydrocarbon, all right, if I have a compound with carbon and hydrogen in it, and I burn it, and remember in chemistry burning just means we're combining it with oxygen, okay, and the products are going to be H2O and CO2, all right. That also applies if there is oxygen in this initial substance as well. Our products would still only be H2O and CO2. Now, the key thing to remember in our method of solving this is if we look at our unknown substance, all right, here is the carbon, and what do we notice about our products? Well, we notice that all of the carbon from the substance is going to end up in that carbon dioxide. And similarly, all of the hydrogen from that reactant is going to end up in the water. And so if we know how much water was produced, I can go either through a factor label calc or through a percent composition calc. I can find out how much hydrogen was in the original carbon based on how much water was produced. Same thing with the carbon. I can look at how much CO2 was produced and determine from that how much carbon was in the original component. Now, if there was oxygen in the original component, I couldn't do a straightforward calc like that, just because in order for this substance to burn, I'm actually adding oxygen to it. And so the oxygen that's in the water and the carbon dioxide can come from the oxygen that I'm feeding into the apparatus, or it could have been part of the initial compound if the initial compound had oxygen in it. So we'll add a little step to figure out the oxygen. But essentially the thing to remember is we're really only calculating an empirical formula, and when our data is given to us this way, where we have a mass of water and a mass of CO2, that there's just an initial step we have to do to get it into a simple empirical formula calc. All right, so again, we're going to convert the data that we get, which the data we're going to get is going to be grams of water and grams of CO2. Okay, we're going to convert that into grams of carbon, hydrogen, and oxygen if we know it's present in the substance. Then we're going to determine the empirical formula the same way we did before. And then if we know the molar mass, we can use the empirical formula with the molar mass to find the molecular formula. So we're just kind of adding a little thing up front with this. So let's look at an example problem. Here I have a compound, trioxane, which has carbon, hydrogen, and oxygen. And the data, I have two experiments. One where they burned it and got a certain amount of water and carbon dioxide, and then the second experiment they found the molecular mass.
There are several different ways that we can determine how many grams of hydrogen are in the 10.477 grams of water and how many grams of carbon are in the 25.612 grams of CO2. I think the simplest way is just through a straight mass ratio. So I can ratio my grams of water to grams of hydrogen and then set that up where I'd use the molar masses of grams of water to grams of hydrogen. So molar mass of water and there's 2 hydrogens, so that would be 2.016. And then the same thing over here, ratio grams of CO2 to grams of carbon, and I get grams of CO2, grams of carbon, and so the molar mass 44.009, and there's 1 carbon, so 12.011. All right, so if I solve that ratio, then I'm going to get, let's see, 10.477 times 2.016 divided by 18.015. Okay, so I get 1.172 grams of hydrogen, and then 5.612 times 12.011, and then divide by 44.009. So I get 6.99 grams of carbon. And then if we look at those two values, we see that they don't come close to that total. So it did tell us it had oxygen in it. So the remainder of that mass, of our total mass there, must be the oxygen. So to get the oxygen, I'm just going to subtract the hydrogen and subtract the carbon, and then that's going to give me 17.471 minus 1.172 minus 6.99. So that's going to give me 9.309 grams of oxygen. Okay, so that's the only thing that we have to do different, this additional step up front, if we're doing an empirical formula calculation, but we're getting the data from a combustion analysis.
So let's transfer these numbers. So I have from before 1.172 grams of hydrogen. I have 6.992 grams of carbon, and I have 9.307 grams of oxygen. Okay, so same process as before. Convert it to moles. Remember to carry it out. Don't round it too soon. Okay, so here's our smallest. It's going to be 1. That's going to be about 1, and then this one. Is going to be approximately 2. So my empirical formula then is going to be CH2O. All right, and then I'm going to have to go back a slide here because I didn't write down my molar mass. Molar mass is 90. All right, so now I'm going to go, my molecular weight is known to be 90. And the mass of my empirical is 30.026 grams per mole. So if I take my mass here divided by the mass of the empirical, that's going to give me approximately 3. So my molecular formula is equal to C3H12O. H6O3. You just multiply the subscripts by the 3. Okay, now in this initial discussion, we really didn't come across any problems where these numbers here were not close to whole numbers. Tomorrow in class, we're going to look at some examples of what do you do when those numbers are not close to whole numbers. And so I will take any questions that you have on the stuff that we've covered in here, and then we will add on to this discussion tomorrow in class by looking at how you deal with when those numbers are not whole numbers in that final calculation.